Hey, well, welcome everybody. Thank you for coming along today. My name is Paul Andrew. I'm a Senior Program Manager in Office 365. I'm joined with Paul Collins, who's also a Senior Program Manager in Office 365. And we are both very passionate about network connectivity for Office 365 customers connecting to our services. And so today, we have 45 minutes and we're going to take you through connectivity for the three major workloads, that being Exchange Online, SharePoint Online, and Skype for Business Online, and just exactly how they connect from your PCs and your organization into our data centers. And I hand over to Paul, who's going to kick us off.
Thank you. Hi, everyone. So just to set the scene to start with, I'm going to talk about... okay, my fault. I didn't turn it on. I'm just testing the guy at the back. So, to start with, I'm just going to kick off and talk about a set of Office 365 connectivity principles that we have sat and thought long and hard about to deliver quite concise guidance around what you should drive towards for connectivity to the service. And by doing this, it enables you to fully embrace the changes and the improvements that we roll out over time. And you'll see these in the three workloads we're going to talk about. And it also abstracts you from that change. So you're not constantly having to re-architect things to work with new services and changes in services. So to walk through them, the first one is identify and differentiate Office 365 traffic. So we have a URL and IP page, which is updated roughly once a month on a set schedule. And that outlines the endpoints required per service, whether they live on Microsoft's infrastructure or not, and we provide IPs for those endpoints where we can. Now, the reason why you need to take a close look at those endpoints is to understand what they're doing and whether the management of those endpoints can be done through your standard method of going through a proxy or standard egress, or whether you need to do some sort of special control of them to get the best out of the performance of the service. Secondly is egressing Office 365 data as close to the user as practical. So what that means is not backhauling through to a central egress location where we've got a local egress available. And the reason for that will become clear a little later on. I think part of the issue with explaining this is we haven't done a massively good job in the past of talking about Microsoft's infrastructure that we have in place to improve the service and connect you to your data. So once you understand that, this principle makes a lot more sense. The other point of that is DNS resolution close to that egress. Again, as we talk through the workload, you'll see why that's important. Essentially allowing us to connect you to local services. Thirdly, avoiding network hairpins. So again, same sort of principle as I said before, not coming back into a central location to come out again, or not using a forced VPN tunnel for your roaming users to bring them into your network and come back out again, wherever that's possible. And finally, this kind of links into the first one. Assess bypassing proxies and traffic inspection devices, which duplicate security that is already provided in the application layer. Those of you that were in the session this morning, delivered by Jeff Mielif and Kostya Rifkin, would have heard around the principles around this, that Office 365 is secured at many layers in the actual application layer. And we often see that what a proxy does, or a standard network egress, is just duplicating that service that's done in the back end. So if we give you an example, AV scanning done in the back end, DLP can be done in the back end, and so on. So it's worth looking at those endpoints you identified in the first principle and seeing whether they need to be put through this processing and bottleneck inducing egress through your environment. So with those principles in mind, I'm going to step through and talk to you about that infrastructure that I mentioned, and what we have to connect you to your data. So firstly, just have a think about what Office 365 looks like and how it differs from a standard model of you build a data center, you put your data in it, and you connect your network to it. That whole process doesn't apply when we're looking at Office 365. Your data goes into one of these regions. If you select a location when you spin up a tenant, basically your billing location, so we're in North America, then your data will reside within that region. But it's in multiple places, so designing networking to connect to a place no longer really applies. And further to that, you may have global sites that need to connect to that data. And once you understand the infrastructure Microsoft's got to connect you to that data, then again, thinking about networking to where you think your data is doesn't really apply. So that infrastructure, you've probably heard it in a couple of other sessions. I just heard it one just before here. But Microsoft has one of the biggest global networks in the world. So I think, for me, it's one of our greatest unsung assets. We use it for Azure, for Office 365, for Xbox Live, to connect you to your data, wherever you are in the world and wherever your data is in the world. So those dots on the screen represent peering locations where ISPs hand off traffic to Microsoft's network, and we take it the rest of the way on our own network. That network is constantly growing, being updated. It's very high bandwidth, low latency connections. It's designed for our services. So we want your traffic on this network as quickly as possible. The other thing we're doing as well is moving elements of services or optimizations to where those dots are, or to the data centers within region. There's a few stats on that network. It's managed by our Azure networking team. It's one of the top 2 networks in the world, I'm told, by the Azure networking team. As I said, very, very high bandwidth, low latency, failover capable links. We can survive a cable cut, or in most instances, 2 cable cuts. Without you really noticing that it's happened, we run these links at low bandwidth utilization. We plan very far in advance to make sure that those circuits can cope with any sort of condition that's thrown at it. I found a stat yesterday that the fiber optic network in that backbone can stretch to the moon and back 3 times. So it's a considerable amount of infrastructure that's in place. And as I say, something we haven't traditionally talked too much about. And importantly, to make that connection to you and your ISP, we have peering agreements with over 2,500 ISPs globally and in 38 countries. I'll show you where those points are. You can look them up. That's public information. But essentially, part of the troubleshooting and performance drive that we talk about with customers is getting your traffic on that network as quickly as possible. Then we can optimize where we can deliver local services, and we can get you to your data as quickly as possible. And just to give you an example of how that's constantly growing, you may have seen this. It was released in the news recently. Microsoft have partnered with Facebook and a few other partners to build an undersea cable between Europe and the US. Don't necessarily need that currently. Our links over from Europe are very good and we don't have any issues with them, but that's planning much further ahead in the future. For example, we have data centers going online in France, South Africa, and other ones in planning in the future. So these things take a long time to implement. But you can see some of the stats there. This is 160 terabytes a second, 16 million times faster than an average home internet connection, or if you're staying in the same hotel as me, about 1,000 times faster. And that infrastructure, as I say, is something that we're constantly adding to and improving. So in terms of where we peer, you may not be able to see this from the back, unless you've got super eyes, but the slide deck's available after the session, and the link there at the top will take you to Peering DB, where you can search for, well, that search will take you for our ASN, our network number 8075, and you can have a look where Microsoft has presence, who else is in those locations, and so on. But you can see we've got presence in many metropolitan areas around the globe. And I've consolidated this. We have many points of presence in London, for example. We have more than one. We've only listed it once there for brevity. So we can actually see very easily how your traffic's getting onto this network. So I asked a few colleagues around the globe to do a trace route to a tenant that I gave them. This is the one I did from my home in the UK. I've gone over my ISP network through hops 1 through 6 there. I'm on Microsoft's backbone actually in hop 7. I don't have time to explain how I know that, but the important thing is in hop 8, we're on Microsoft's network. You can tell that because it says msn.net on the end of the router name. That's Microsoft's network. And the other thing you can tell, highlighted in the middle, LON04. So we're on Microsoft's network in London, which is a sensible place for me because I live 40 miles to the west of London, in 26 milliseconds. Funnily enough, since I first used this slide, my latency's down to about 15 milliseconds. So I think BT may have been listening to me when I presented this in the past. So thank you if you did do that. So a colleague in France connecting to the endpoint, we can see the same thing happening. Here in hop 7, in 8 milliseconds, and we can see PAR02, Paris. We're on Microsoft's backbone, and then that can be taken to wherever it is in the world. We can actually tell where it's going because the last router name is AMS04, Amsterdam. Here's another example from Florida. So this was from a user's home in somewhere in Florida. I can't remember, Tampa by the looks of it. And then in hop 10, we're on Microsoft's network in Miami in 24 milliseconds. Again, excellent. That's what I want. On Microsoft's network as quickly as possible. And we take it the rest of the way from there. So here's an example of where that's not quite gone to plan from a customer that I was with in Scotland a while ago. So that should peer in London. That's the obvious place for somewhere from Scotland. But you can see on the ISP network, we've come through London, all good so far. And then hop 7, we're in New York, still on the ISP network. We bounce it around, and then finally in hop 12, we hit Microsoft's global backbone in New York. We look at that endpoint and say, well, that's in Europe. Let's take it back over the Atlantic. And this was just an example where the ISP is not paired with us very well. And if you spot something like this that is obviously wrong, let us know, let your ISP know, and we can work to fix the problem. It's thankfully very rare because we do proactive work in this space, and as I say, we pair with over 2,500 ISPs globally. But the important thing is to understand that Microsoft has this reach globally. Your traffic is not on the internet for very long, ideally a short number of hops, a short number of milliseconds. And thinking about the latency to the endpoint, this is actually getting a little more difficult to give you accurate numbers on because of the way the service is changing. Most major workloads now don't connect directly to wherever your data is. We don't connect a unicast connection to your SharePoint tenant, for example. We use edge nodes, front doors. You might hear them referred to with various different names. So for me, the key is to look at that peering we just showed. Are we peering in a sensible location in a sensible amount of time? Are we peering in the right location? To give you a rough idea of what to expect, and again, this will make more sense as we work through the workloads, but about 100 milliseconds total is a very generous number, but I've kind of had to cover all scenarios. You should really be hitting the front door of a service in probably half or less of that in most cases, especially in metropolitan areas like in Europe and in the US here. But there are occasions where the distance between the client and the front door is quite a long way. China, for example. It may take a fair amount of time to get to the nearest peer point, which is in Hong Kong, because we have none of those peering points in mainland China. And with that, Paul's going to walk you through how Exchange Online connects and how those principles means that you can consume the benefits of how this service connects instantly.
All right. So we're talking about this information and sharing some of this with you because, well, Microsoft spends a lot of money and a lot of time in optimizing how our data centers work, how our network that Paul's been telling you works, how fast that is, how available that is, so that you can get great performance. But something we don't have influence over is the internet. We don't have influence over that, And of course, we're not going to come into your organizations and change your networks and do those things. So we want to give you this information that we're talking about today so that you can spot connectivity issues between your users and our network and our front ends. And we want to make it as easy as possible for you to see those things and be able to do something about it. We find when we work with customers, there's all sorts of variety of different networks that people have, and connecting to SaaS applications like Office 365 is not always the same or as what people are familiar with. So hopefully with this deep dive into these workloads, it'll help you to be able to do that, to see, aha, this doesn't look right, I'm going to dig into it a little bit more, and I remember how they said it should work and what those numbers should look like. So Exchange Online has two major clients that we want to talk about. The first one is Outlook Web Access, and the second one, of course, is the Outlook client. Now, Exchange does have other clients, but we're going to focus on these two because they're the primary ones that people use. They have the most data transferred, and so they tend to be the most, they require the most help with connectivity. So we have front-end servers, two types of front-end servers that host these two clients. We actually have front-end servers called Edge servers, or otherwise called Azure Front Door, which are used for Outlook Web Access. These servers are Anycast IP identified, so there are a small number of IP addresses which are repeated on a large number of these Edge servers all around the world. So wherever you are connecting to Outlook for OWA purposes, you're going to be connected through BGP routing to the closest of those IP addresses. That's what Anycast is, that's how that works. The cafe servers that we use for Outlook client use unicast IP addresses. So there's a single rack of servers represented by a single IP address. And so the Outlook client connects to one rack of cafe servers somewhere. And how we identify where that rack of cafe servers is important because we want that to be something that is close to the user of Outlook. So we'll spend a bit of time, because a lot of that is under your control, whether that's working well, we'll spend a bit of time talking more about how that connectivity works. So first, at a high level, there are three parts to identifying a cafe server that Outlook wants to connect to. First, we've got app discovery, and then name resolution, and connecting to the cafe server or the client access front-end server. So your Outlook client is going to do app discovery by using auto discover, and for Office 365, almost all of these are going to point to outlook.office365.com. And then we have to look that up in the DNS. And there's a few hops that might happen, and there's a few differences you might see when you're using DNS. We have a couple of different types of DNS servers that I'll talk about very briefly. The first is a forwarding DNS server. If you're using a forwarding DNS server, when you set that up, it only needs one IP address, which is the DNS server upstream that you forward all requests to. It's very easy to configure, it's very simple, and it just requires another DNS server to connect to. It doesn't actually do any lookups itself, and it's very common. The second one is a local DNS server. It's sort of referred to as a local DNS server, but this is a server that's actually configured, secured, and does DNS lookups to the name servers that are authoritative and actually own the DNS zones. The third one is the authoritative DNS server. That's where the data comes from, the information about your URL to IP address mapping. And so we need to identify where is this local DNS server, because the authoritative DNS server uses a mechanism called GeoDNS. It's going to try and figure out where is this request coming from, and therefore where should I send the client request to. So it's important that that local DNS server be nearby or in proximity to the Outlook client. It's no good to have a forwarding DNS server nearby because the authoritative DNS server doesn't get that IP address. So we have this concept of locality specific to that local DNS server. Once you've done that, you can get an IP address, you can connect to the client access front-end rack, and that is a termination of your TCP connection. If you do a ping or a trace route, that's what you're going to be connecting to, and that's what Outlook connects to. Our mailbox servers are actually housed separately in Microsoft data centers, but we can look after that, we can manage that and optimize the performance. We'll do our best to make sure those are as close as possible to you in the future, and we can optimize that network connectivity. So a key thing here is configuring DNS. Let's talk a little bit more about how that works. We actually use two systems for DNS or GeoDNS today, and we use these side by side, and we do this for high availability reasons. Just in case one system goes down, there should be no impact to Office 365 users. We actually had a case of this last October. One of the DNS systems we were relying on went down, got taken out by a DDoS attack. It was actually a third-party system. Office 365 users weren't impacted because we had this other system for high availability. So the first one we have here uses a technology called Global GTM, or Global Traffic Manager. And GTM, you can see in the middle of those DNS servers there, the Global Traffic Manager DNS servers, they take a request for a DNS CNAME that we provide, and they look at the IP address of that local DNS server, and they will return another DNS CNAME which identifies where in the world approximately that request came from. They have tables and they do these lookups. And so in my example on the slide, you can see the GTM server. The GTM DNS server has returned outlook-au.office365.com. And when we were only using the system, or if you hit this system today and you're in Australia, you should see, if you hit it with ping or traceroute, you should see the resulting server appear to be called outlook-au.office365.com, and many other names representing other regions around the world. And then there's a final DNS lookup on that URL, which will return IP addresses, and we connect. Now, how do you debug this? Well, you've got to make sure that local DNS server is close to the client. The way you can test that is really easy. You could just look at the URL that comes back when you do ping outlook.office365.com. If it looks like a name which is nearby to where your users are, it should be good. If it doesn't, if it looks like it's on the other side of the world with these shortcodes that we use, then you've probably got something you want to troubleshoot in your DNS or your routing that's causing that. All right, so let's talk about the second method we use. And we currently, you will see both of these methods when you're connecting to our front ends today. The second method is using a DNS server which actually has an Anycast IP address and is located on the same racks as our cafe servers, our front end servers. Now remember, Anycast IP addresses means when the client tries to do the lookup, tries to connect to it, it will connect to whatever server advertising that specific IP address is closest by BGP routing. And so it's going to make a request of this URL, outlook.ms-acdc.office.com, and whichever DNS server is closest is going to return IP address results. And that's going to be IP addresses which relate to the rack that DNS server is on and other very close nearby racks. We can actually provide much closer racks than with the GTM model because we have an advantage in how we can provide HA with this DNS system. If we have an issue with a rack of cafe servers, we can literally take the DNS server, which is at the top of the rack, out of the name system. We can remove it out of there and you'll no longer get results from that rack immediately. We can't do that with the GTM system because that would involve actually updating the DNS and propagating that around the world. So with the GTM system, we actually have to return IP addresses of servers that are quite geographically dispersed. In case one of those has an outage of some size, then Outlook will move on to the next one. Now, that's not a requirement with this Anycast system. So we get an advantage by that. We can give you a closer front-end server. One downside of this is you can't check that your DNS is working by just looking at the result of ping to outlook.office365.com because this system always returns that single URL. So what you have to do in order to test this is you've got to look at where the IP addresses are located. You'll get some IP addresses back. You've really got to figure that out, which you can sometimes do with ping and traceroute. Sometimes you've got to do it by using a geo IP service. If they're in the wrong region, you're going to want to follow up and see something might be wrong with your DNS. All right, so two summaries on Exchange. First, for client latency, the actual milliseconds or ping time that you see, you want to make sure you're using Outlook cached mode, not Outlook online mode. You want to seek to minimize that latency that you have. There are some non-cached operations even when you're using Outlook in cached mode. So if you have very long latencies that you're seeing, some users with these particular operations are probably going to notice that. In order to get your DNS going well, you want to make sure that you know the location of that local DNS server. It doesn't help you to know the location of a forwarding DNS server. And you're going to want to know who owns that, where it is, follow up with them if you have any issues with it. If you don't have a local DNS server that you know about that's reliable for you, you can set your own one up, make sure it's secured, configure it with root hints, and it's going to be doing those lookups directly. And just a point to avoid a global DNS forwarder. If you have a local DNS server in one point in the world and those results are being cached globally and your users are getting those, we're going to think that all your users are in that one location in the world. So try and avoid those. All right, I have a quick demo to look at. Before we started the talk, I ran traceroute to outlook.office365.com a couple of times. The first one here, you can see that it says that I'm tracing the route to outlook.ms-acdc.office.com. This tells me that we're using this Anycast DNS server, which is on the cafe racks, and so I like that. If I follow down this trace, I can see that my ISP, this is literally done in the room here before the talk, my ISP is peering with Microsoft in Miami, MIA01, I can see. Actually, I'm not sure about that.
It's probably hop 11, but
yeah.
The next hop is hop 12, where it's in Atlanta.
Right. And actually, hop 12 and hop 13, both in Atlanta, is the last location that I can see. And there's a pretty good chance that is where the cafe server is that I connected to. The other one here that I've got, I did it again. And it says I'm connecting to outlook-namcentral.office365.com. So if we scroll down, I can see in this one MIA-96CBE-1A, that's in Miami. And then if I go a bit further down, it looks like I'm actually using a front-end server in Wyoming. So I've gone to a slightly different place, but I'm using that different DNS lookup. All right, switching back. Here you go.
Okay, so that Anycast system is pretty new. I think this is the first time we've publicly talked about it. And it's an addition, a change to the service to help improve performance and give us greater capability in terms of failover, etc. Kindly, the Skype team have allowed me to talk about a change which they're implementing now. There's a couple of sessions which go into great detail about this week, and I've linked those at the end. Certainly worth watching if you have the time. But let's have a look at Skype for Business and how its connectivity model is completely different to how Outlook connects to its Exchange Online service. But if we follow those principles we mentioned earlier on, we can fully utilize all these benefits and the changes. So Skype, for me, well, not for me, for anyone, is the most sensitive to network connectivity. It's real-time media. Exchange is really hardy in cached mode to network issues. Skype, not so much, because we've got to get those packets to the listener, the viewer, in real time. So in terms of connectivity, we need to understand the IP endpoints, the ports that are open. I'll talk about the ports in a second. Important for Skype to be able to work at its best by using UDP. Bandwidth issues are always important for all services, but again, can introduce things like jitter and packet loss if we have problems. And I'll actually show you what it looks like on the network here with 25,000 people on it, just handling it relatively well. And with hybrid, as with any other service where we've got a hybrid, identifying all the inbound and outbound network flows is key to making sure the traffic flow is going in the most optimal way. So let's just look at how Skype actually works. You sign in. The signaling traffic will go to a pool in the location of the tenant. So if my tenant's in the USA and I'm in Europe, I'm going to have a TCP port 443 connection to that tenant. And that connection is going to inform the client of the relay to use for my media services, for my calls and videos. When we initiate a media call, what happens depends on the scenario, and we'll walk through that in a second. But it uses three methods to try and connect From top to bottom there, it uses UDP direct. So if you have the UDP ports open, and the Skype team have done a great job of improving things here. We used to require ports 50,000 through to 59,999, which was a big ask of a security team to open that up in an external firewall. You now don't need those ports open. We'd prefer if you did. There's some optimizations can happen if that's the case, but you only need 3478 through to 3481. So if we can connect that way, then we use that. We also try at the same time port 443 over TCP. Skype doesn't prefer TCP because of the protocol. With UDP, if we lose packets along the way or they're out of order, it doesn't really matter. We can fill in the gaps with the software very, very easily. With TCP, we have to deliver every packet in turn, and that kind of reduces the ability to do that. And finally, if we have to, we'll use a proxy. This really introduces the high risk of jitter and other problems. Essentially, if we get a response from the top, we use that. We get a response from the middle and not one from the top, we use that. And finally fail over to the bottom. In terms of mapping for those connections, I've just put this in here for reference. These are all on the URL and IP page that I mentioned earlier on. But yeah, it's a relatively small number of ports required for Skype for Business now. But in terms of connectivity, as I said earlier on, it depends on the scenario. If I'm on a flat network in building 40 of Microsoft, Paul's in building 30, we should have a flat network between us with no firewalls or anything else. So we can do a peer-to-peer call using Skype for Business. That traffic never goes out to the cloud, doesn't need to bounce off a relay. It just goes on the network between our 2 points. When we start to look at connections between two users that aren't on the same network, then currently this is the model. So Skype will connect to the media relay server that sits in the tenant location where my tenant resides. So that example I said earlier on, I've got 2 users in Europe here, one in Germany and an employee in Ibiza on trying to call in sick. So we have a call between those 2 people. Because they're on separate networks, it has to bounce off the media relay server in the USA. Now, this is fine. And you'll notice this customer is using the right principles. They've got local egress, the red line from the user to the dot, and those dots represent edge nodes of Microsoft's global backbone. So we've got local egress. This is great. This performance should be fine. We'll have fine core quality, meeting quality, all good. But what Skype are rolling out currently, again, they'll talk about this in more detail in the sessions later this week, is something called a transport relay. So now, if this tenant is enabled for this, what's going to happen is we have the same call between these 2 users, but now we can bounce off a transport relay in a data center in Europe. Even though my tenant's in North America, I'm not having to traverse the Atlantic with this traffic, with the obvious benefits of not having to do that. But this is only possible because this customer is using those principles with local egress. That traffic's on our backbone very quickly. We can then route it to the nearest transport relay, and doing DNS locally helps with this as well. So you can see how each of the workloads is changing. We're adding improvements all the time, and you'll see the same with SharePoint in a second. And if we followed those principles, these are instantly consumable. It's probably worth pointing out something called multi-geo, which we've announced or announcing this week? Announced, good, right. Phew. Currently your data is held in the location when your tenant is, but that's going to change if you sign up for multi-geo. You can move the user's mailboxes, for example, to Europe. And if we've got local egress, we can instantly consume that. But if my network for this company is in the USA, because that's where my head office is, pointless. There's no point moving my data to Europe when my network egress is in North America. So just to quickly look at Skype's performance requirements in terms of connectivity to the service, the Skype team have a really clear set of guidance about what will constitute a high-quality call and meeting in terms of network latency, burst packet loss, inter-arrival jitter, and packet reorder. Now, these things can be quite hard to kind of get a figure on. So the Skype team have written a tool which does exactly this. It measures all these figures and spits out a report that says pass or fail. It's available from that short link there, and it bounces off Skype's worldwide Anycast IP. What we recommend for customers when looking at this is run the tool at a client location and also at your network edge, because there's two sets of figures if you look at the previous slide. And what doing that allows you to do is see if any problems exist outside of your corporate network or inside. And then we can do the work that needed to fix that. So normally what we recommend in terms of getting you a good view, run it for 1 working week on the client and the edge. Run it every 5 minutes, and it uses the 90th percentile to get rid of the top and bottom results to give you a good average. So I'll give you a very quick demo of this.
You're 8?
Yes. Oh yeah, if anyone's got calls with me this week, my son's taking them for me. Probably doing a better job as me as well. So the tool's really simple. You download it, run the executable. There's a config file where you can tell it how many iterations. It does a 17-second call, and it measures all those figures. So running it over a long period of time will give you an idea about whether your network can cope with these requirements over that time. I ran this with the wired network here just before we started talking, and you can see, let me zoom in a little bit if I can. There's two sets of results here. The top one, I think, is the client. So if this is a client that's far away from its egress, then it's past the top 3, but we've got reorder issues for some reason. We'd have to look into that. If it's run at the network edge, then it's failed the packet loss rate. Latency and jitter are okay, which is pretty amazing given the amount of people on this network. But this would indicate to me something's not quite right, and I'd like to look into what's causing this. It's essentially using those figures I showed you before, aggregating the results, and then putting it through. So you can actually see at the top here the figures. So it's just referenced those against those Skype for Business framework figures, and then giving you that result of pass or fail. So it's a really good tool to get an idea how your network's standing up for Office 365 traffic. And in my point of view, if it's good enough for Skype, it's good enough for the rest of the services.
All right. Come up. Okay, so the last workload here we're going to talk about is SharePoint Online. And connectivity to SharePoint Online is pretty straightforward. SharePoint Online uses Anycast IP address technology as well, and they have a whole lot of front-end servers all around the world. So when you connect to tenantname.sharepoint.com, your DNS lookup is always going to return this one IP address, 13.107.6.151, wherever you are around the world. Now that's represented by a whole lot of different servers, edge servers, running on Azure Front Door, and they are all advertising routes, or the routers next to them are advertising routes in BGP to the same server. So wherever your client is, it's going to receive maybe multiple routes to get to that IP address. It just thinks there's multiple paths. That's how Anycast works. It thinks there's multiple paths to get to a single server for a single IP address. So it's going to pick the shortest one, and the shortest one happens to be the closest IP address that you've got. So that's how that works, and we terminate TCP and SSL connections on that Azure Front Door server, and we get a number of benefits from this. The first is that SSL has about 6 round trips. For TCP and SSL to get set up, there's a lot of to and fro from the client to the server. And if we can shorten that distance, we can speed up that connection time. The second is just the TCP IP protocol is kind of slow when there's long latencies involved. And by shortening that distance for that termination of the TCP protocol, we can make file uploads and file downloads actually perform significantly faster. The third is, although Microsoft's global network has peering locations all over the world, and we're going to attract traffic onto that network, that's not the same decision that's being made about the return traffic. So your forward traffic, if you're connecting from a client to a faraway Microsoft server, is going to get pretty quickly onto Microsoft's network, and that packet's going to go to our server on our network. The return traffic is going to look for a route back to your client. which might be over our network or might be over the internet. By having an edge node like this, we know that that traffic is going to go back to that edge node, and then it's on the Microsoft's network, and then it's going to go back over the internet to your client. So let's take a look at a couple of examples. Here's a client machine in Europe and a SharePoint server in North America. And first, we're going to do that lookup on tenantname.sharepoint.com. And this is the previous unicast model, which you shouldn't see today, but it would return the IP address of a server in Microsoft's network co-located with the SharePoint farm where the SharePoint data is. And so your connection has to go from the client in EMEA across to North America. That SSL setup has got to be done across the Atlantic, and you're going to get a response and you're going to be connected. So with the new model, we've got that same client in EMEA. They do a lookup in the DNS to tenantname.sharepoint.com, and they return that single IP address, that Anycast IP address. And then that address is represented on a number of these edge servers. And those edge servers have hot connections that are already set up back to the SharePoint farms. And so you're going to get that connection much faster. Let's take a higher level look at how this might work. A user in the US is going to connect onto Microsoft's network and onto an edge node and then onto the SharePoint farm. And they're going to get there pretty quick, basically a straight line here. We're always looking for a straight line in networking. We want to get that fiber stretched out and not have it go all over the place. For the user in the UK, when they connect, they're going to be making a connection onto Microsoft's network. Let's say that first dog leg is getting onto Microsoft's network, but then the whole connection has to go across the Atlantic onto our SharePoint farm. And then if they do that with the new model using Anycast, they actually make the connection to an edge node over in Europe, and that's the end of their connection. That's all they need to do. Although the data still comes back from the US, we're seeing just enormous performance increases for using Anycast and these edge nodes. We're seeing up to 10 times an increase in performance of file downloads where users are in a different region to their SharePoint farm. So that 10x really is looking at the longest latency that we previously had and shortening that latency by terminating the TCP connection and SSL.
I'm quite a cynic, and when the SharePoint team told me that data, yeah, whatever. But I went and tested, and those figures are pretty much correct. I've validated it myself.
All right, so let's take a look at what you see and what you can debug in terms of connectivity to SharePoint Online. So we showed some trace routes before. Here's some trace routes of connecting to that single IP address, 13.107.6.151. And the first thing you see here is the yellow highlight. This is Paul's home, Paul Collinger's home, connecting to SharePoint Online. And you can see that his traffic is peering in London. That's what that first thing says there. And you can see the other yellow highlight, msn.net. That tells you it's Microsoft's network. And then you can see the last router is identified as AMS04- some other numbers. AMS for Amsterdam. And so this is connecting to a host in Amsterdam for paulcole.sharepoint.com. If we do the same thing in Sydney, and this connection is actually on a cell phone, so it's a 3G connection in Sydney. You can see that same trace route to 13.107.6.151 again, and the trace route is to paulcole.sharepoint.com. But here, the peering happens in Sydney, and that's actually the last router that we see. That's the first one on msn.net. So it looks like the SharePoint farm, in this instance, is actually in Sydney. And this is just showing us terminating that TCP connection and that SSL.
We flew all the way to Sydney to get that trace route for you, by the way.
Yep. All right, one more. So this is a user in Charlotte. By now you're getting the gist of this. They are peering in Atlanta. We can see ATB as the key there on msn.net. And then BL2, it looks like they're terminating their connection in Washington, D.C. So it's a nice close node there for the user in Atlanta. Paul, where is this SharePoint farm?
In Europe.
Right. So either way, it's across there in Europe, but we get that performance improvement by terminating those TCP connections. Quite amazing the difference that makes.
But only possible if you follow those principles of local egress.
Right. So we want to talk more about these principles of connectivity to Office 365. And we had an architecture strategy talk this morning that we mentioned before. Konstantin and Jeff presented that, so you can check the recording of that. Paul and I actually have a planning session on Thursday where we'll deep dive into those connectivity principles, what you can do for planning to follow those. And we actually have a meetup on Friday. We'd love to see you there. We'll talk about some case studies of large customer WANs and typical questions that come up. We've also got some sessions here that we want to plug for network connectivity details from specific workloads. Skype for Business have a couple of sessions, 4004 and 3029. SharePoint have one on Thursday, where they'll talk a bit more about their connectivity. And Exchange had one on Monday, really great talk, which I watched, and I encourage you to check out the recording of that as well. So thanks very much for showing up today for our session.
And yeah, if you get the time, we'd really appreciate the feedback through the app to help everyone plan with sessions next year. You know, if you like the session, let us know. If you don't, let us know, and we can make sure we deliver the right sessions for you next year. Okay, thank you very much.